Welcome. Today we're diving into the world of pseudocode and its role in algorithm design. Whether you're a beginner or brushing up on your skills, understanding pseudocode is essential for clear and effective problem solving. Pseudocode acts as a bridge between human language and programming code, allowing us to outline our ideas logically before translating them into a specific programming language. Throughout this video, we'll explore what pseudocode is, why it's important, and how it helps us develop algorithms step by step. Let's get started by defining pseudocode and seeing how it fits into the bigger picture of algorithm development. Pseudocode is a way to describe algorithms using plain language mixed with programming-like structure. It's not bound by the syntax of any specific programming language, making it easy to read and understand. Think of pseudocode as a set of instructions that anyone with basic logic skills can follow, regardless of their coding background. By writing out the steps of an algorithm in pseudocode, you can focus on the logic and flow without worrying about technical details. This makes it a powerful tool for planning, teaching, and communicating ideas clearly. Why do programmers and computer scientists rely on pseudocode? The answer is simple. It helps break down complex problems into manageable steps. Pseudocode allows you to map out your logic before diving into actual code, reducing errors and misunderstandings. It's also a universal language for teams, making collaboration easier. When everyone understands the plan, it's much simpler to assign tasks and spot potential issues early. Whether you're working alone or with others, pseudocode streamlines the development process and ensures everyone is on the same page. Like programming languages, pseudocode doesn't require strict syntax or rules. You don't have to worry about semicolons, brackets, or variable declarations. Instead, you focus on the logic and structure of your algorithm. This freedom allows you to express ideas quickly and clearly. Once your pseudocode is solid, translating it into any programming language becomes much easier. It's like sketching a blueprint before building a house. You lay out the plan before getting into the technical detail. Pseudocode typically follows a simple, logical structure. You write each step of your algorithm in order using clear and concise statements. Common keywords include start, end, if, else, while, for, and print. These help organize your thoughts and make the flow of the algorithm easy to follow. By keeping things straightforward, pseudocode ensures that anyone reading it can understand the intended process without confusion. Let's look at some of the most common keywords used in pseudocode. These include start and end to mark the beginning and end of your algorithm, if and else for decision-making, while and for loops, and print or output to display results. Using these keywords helps structure your pseudocode and makes it easier to convert into real code later. They act as signposts, guiding you through the logic step by step. Ready to write your first pseudocode? Start by outlining the problem you want to solve. Break it down into clear, logical steps. Use simple language and the keywords we just discussed. Don't worry about programming syntax, focus on the flow of the algorithm. As you write, ask yourself if someone else could follow your instructions without needing more information. If the answer is yes, you're on the right track. Let's walk through a simple example, finding the maximum number in a list. In pseudocode, you'd start by setting a variable to hold the maximum value, then loop through each number in the list. If a number is greater than the current maximum, update the maximum. At the end, print the maximum value. This step-by-step approach makes the logic clear and easy to implement in any programming language. Here, how the pseudocode for finding the maximum number might look. Start. Set max to first number in list. Or each number in list. If number max, then set max to number. And if for print max. And this format is easy to read and understand, making it perfect for planning and communication. Another classic example is calculating the factorial of a number. In pseudocode, you'd start by setting a result variable to 1, then multiply it by each number from 1 up to the target number. At the end, print the result. This logical sequence is easy to translate into any programming language thanks to the clarity of pseudocode. Let's see the pseudocode for calculating a factorial. Start. Set result to 1. For I from 1 to n. Result equals result I. for print result. And this simple structure highlights the power of pseudocode to clarify complex operations. Conditional statements are a key part of algorithms. In pseudocode, you use if, else, if, and else to handle different scenarios. This allows your algorithm to make decisions based on certain conditions. For example, you might check if a number is positive, negative, or 0 and handle each case differently. Using clear conditional statements keeps your logic organized and easy to follow. Loops are essential for repeating actions in algorithms. In pseudocode, you'll often use for and while loops. For loops are great when you know how many times to repeat, while while loops are useful when the number of repetitions depends on a condition. By clearly outlining your loops in pseudocode, you make your algorithms flow easy to understand and implement. Handling input and output is straightforward in pseudocode. Use read or input to get data from the user and print or output to display results. This keeps your algorithm interactive and user-friendly. By clearly marking input and output steps, you ensure your pseudocode covers all necessary interactions. Let's look at a searching example. Suppose you want to find a specific value in a list. In pseudocode, you loop through each item, check if it matches the target, and if so, print its position. This approach is called linear search and is easy to express in pseudocode, making it a great way to plan your algorithm before coding. Sorting is another common task. In pseudocode, you can outline simple sorting algorithms like bubble sort. You compare adjacent items, swap them if needed, and repeat until the list is sorted. This step-by-step logic is easy to follow and helps you understand how sorting works before implementing it in code. Here's a sample pseudocode for bubble sort. Start. For I from 1 to length of list 1. For j from 1 to length of list I. For list j plus 1 then. Swap list j and list j plus 1. And if. And for. And if or. Print sorted list. And. This structure makes the sorting process clear and easy to implement. Pseudocode offers several advantages. It's easy to read, language independent, and helps you focus on logic rather than syntax. It also makes it easier to spot errors and communicate ideas with others. By using pseudocode, you can plan your algorithms more effectively and ensure a smoother transition to actual code. While pseudocode is powerful, it does have some drawbacks. Since it's not standardized, different people might write pseudocode in different ways, leading to confusion. Also, pseudocode can't be executed by a computer, so you still need to translate it into real code. Despite these limitations, its benefits for planning and communication are significant. To get the most out of pseudocode, follow some best practices. Keep your statements clear and concise. Use consistent keywords and indentation to show structure. Avoid unnecessary details and focus on the main logic. By following these guidelines, your pseudocode will be easy to read and translate into code. Indentation and formatting are important in pseudocode. They help show the structure of your algorithm, making it easier to follow. Use indentation to indicate blocks of code, such as the body of loops or conditional statements. This visual organization helps readers understand the flow and hierarchy of your logic. One key rule in pseudocode is to avoid language-specific syntax. Don't use curly braces, semicolons, or other programming symbols. Stick to plain language and logical keywords. This keeps your pseudocode accessible to everyone, regardless of their programming background, and makes it easier to translate into any language. Comments can be helpful in pseudocode just like in real code. Use them to explain tricky parts of your algorithm or to clarify your logic. Comments are usually marked with a double slash or a hash, but you can use any clear marker. Good comments make your pseudocode even easier to understand. You can use pseudocode to outline functions or procedures. Start by naming the function and listing any inputs. Then describe the steps the function performs and finally specify any outputs. This modular approach makes your algorithms more organized and reusable. Let's write pseudocode for a function that sums two numbers. Function sum a b. Return a plus b. And if you want CTON. This simple structure shows how easy it is to define and use functions in pseudocode, making your algorithms cleaner and more modular. Recursion is when a function calls itself. In pseudocode, you can outline recursive algorithms by clearly stating the base case and the recursive step. For example, calculating factorial recursively involves checking if the number is 1, then returning 1, otherwise returning n times the factorial of n1. Here's how recursive factorial looks in pseudocode. Function factorial n. If n equals 1 then. Return 1. Else. Return in factorial n1. And if you want CTON. This approach highlights the elegance and power of recursion in algorithms. Arrays are a common data structure in algorithms. In pseudocode, you can declare an array and access its elements using simple notation. For example, set array 1 to 5 or loop through each element to perform operations. This keeps your logic clear and easy to implement in code. Sometimes, algorithms require nested loops. In pseudocode, you can show this by indenting the inner loop inside the outer loop. For example, looping through a matrix involves an outer loop for rows and an inner loop for columns. This structure helps you visualize complex operations step by step. Error handling is important in algorithms. In pseudocode, you can use if statements to check for errors such as invalid input or division by 0. Clearly outlining error checks ensures your algorithm is robust and reliable, making it easier to debug and maintain. Many algorithms involve interacting with users. In pseudocode, you can prompt for input, process the data, and display results. This makes your algorithm user-friendly and ensures all necessary steps are covered from start to finish. Sometimes, algorithms need to read from or write to files. In pseudocode, you can use open, read, write, and close to describe these operations. This helps you plan how your algorithm will handle data storage and retrieval, making the transition to code smoother. Complex algorithms often involve multiple steps or phases. In pseudocode, break down each phase into its own section using clear headings or comments. This modular approach makes your algorithm easier to understand, debug, and maintain. Data validation ensures your algorithm only processes correct input. In pseudocode, use if statements to check if data meets certain criteria. If not, prompt the user to re-enter the data or handle the error appropriately. This keeps your algorithm reliable and user-friendly. Some algorithms require waiting or timing actions. In pseudocode, you can use wait or delay statements to indicate pauses. This is useful for animations, games, or real-time systems. Clearly marking these steps helps with planning and implementation. Randomness is often needed in algorithms such as games or simulations. In pseudocode, you can use random to generate random numbers or choices. This makes it easy to plan algorithms that require unpredictability, like shuffling a deck or simulating dice rolls. Graph algorithms like finding the shortest path can be outlined in pseudocode. Use clear steps to describe how to visit nodes, update distances, and track paths. This makes complex algorithms more approachable and easier to implement in code. Some recursive algorithms have multiple base cases or conditions. In pseudocode, clearly list each case and the corresponding action. This ensures your algorithm handles all scenarios and avoids infinite loops or errors. Modular algorithms are built from smaller, reusable parts. In pseudocode, define each module or function separately, then show how they work together. This approach makes your algorithms easier to test, debug, and maintain. Pseudocode is also useful for analyzing algorithms. By outlining the steps, you can estimate time and space complexity, identify bottlenecks, and optimize performance. This helps you choose the best approach for your problem. Pseudocode isn't just for textbook examples. You can use it to plan solutions for real-world problems like scheduling, navigation, or data processing. By outlining your approach in pseudocode, you ensure your solution is logical and practical before coding. Pseudocode is a great tool for collaboration. Teams can discuss, review, and refine algorithms together before writing any code. This shared understanding leads to better designs and fewer mistakes, making teamwork more effective. Pseudocode is widely used in teaching because it helps students focus on logic without getting bogged down by syntax. Instructors can present algorithms in a clear, accessible way, making it easier for learners to grasp key concepts and develop problem-solving skills. Once your pseudocode is complete, translating it into a programming language is much easier. You already have the logic and structure laid out, so you can focus on syntax and details. This step-by-step process reduces errors and speeds up development. To wrap up, pseudocode is a powerful tool for designing, analyzing, and communicating algorithms. It helps you focus on logic, collaborate with others, and transition smoothly to real code. By mastering pseudocode, you'll become a more effective problem solver and programmer. Thanks for joining us on this journey through pseudocode and algorithms.